Hi, I'm Yike. I'm presenting this joint work with Onno, Malek, Ali, and Michael. In reinforcement learning, environment states are often not directly observable. So to make good decisions, an effective approach is to learn a linear recurrent memory. And this memory gives a compressed representation of the history. But the reason behind the success is unclear. And this is what we try to address in this work. So for this partially observable environment, the state observation dynamics can be described by an action-controlled hidden Markov model with state space X, action space A, and observation space Y. We then have this logit optimal filter LOF, which is the belief over states in the log space, and it provides a sufficient statistic for optimal decision making. In the filter dynamics, AK-1 is the action, Yk is the observation, TAs are action control transition matrices, E is the emission matrix. But for simplicity, we mainly focus on fixed transition hidden Markov model, where the state transitions are fully governed by this fixed transition matrix T. We first studied deterministic transitions. A sample transitions is given here, where state 1 is a transient state, while the others are recurrent states. In this setting, we can reproduce the log results through a linear memory, where R is the number of transient states, L is related to R, P is a permutation matrix related to the recurrent states, C is a nonlinear mapping of the most recent L observations and the time step K. And for action-controlled hidden Markov model, we can construct a similar linear memory with the same performance. We then study nearly deterministic transitions. So the transition matrix here can be decomposed as the sum of a deterministic matrix and some small perturbations. We study the state decoding ability of linear memory, and the arrow is defined like this, with the smallest of the optimal decoding arrow achieved by using LOF. In this setting, we develop an adaptive logit filter ELF. So here delta controls the trade-off between the history and new observations. If delta is chosen properly, as epsilon goes to 0, we also have vanishing decoding arrow. Moreover, the arrow is close to the optimal one achieved by using LOF. And for action-controlled hidden Markov model, we can construct a similar linear memory with the same performance guarantee. To validate our results, we construct a small reinforcement learning game called Ringworld. So there are 12 states, and entering a trap state gives a penalty, and entering a goal state gives a reward. So agents have 4 actions where he can choose to move 1 or 2 steps clockwise or counterclockwise. An agent might overshoot or sleep with small probability. Also, agent can only observe the strongest beacon, and the closer beacons are more likely to be observed. We consider the action-controlled ELF. It gives a strong policy with high return, and it outperforms the widely used deep learning memory called S5. And inspired by ELF, we also develop a trainable linear memory called DeepELF, which also outperforms S5 in this experiment. For more details, please refer to our full paper, and thanks for watching.